notice, and this is the typical copyright. Example 2. We continue with use of graphs as demonstrated by Hooke's law to show line of best fit and extrapolation. So this is the second example. So let's read the question again. A student fixed one end of a spring on a nail and then attached different weights on the other end. She measured the lengths, not extension, the lengths of the spring when those weights were attached. The table below shows the weights and the corresponding lengths. And this is the table. A weight of 1.2 newtons and a length of 0.070 meter and so on. 6.0 newtons, 0.111 meter. So on the graph paper provided, the students were to ensure that the independent variable weight is on the x-axis, scale it out to hold 7 newtons, 7.0 newtons, complete the box with scale and sensitivity, then scale the y-axis to hold 0.160 meter and complete the scale and sensitivity on the y-axis. Then the student were to plot all the given points, then draw a line of best fit. In this case, the last part of the line is curved, and they were to use the graph to find the length of the spring if the weight were 4.0 newtons. Also to find the weight attached if the length was 100 millimeters, and find the length of the spring if the weight attached was 6.8 newtons. Now remember, this graph only goes up to 6.0 newtons. And then also find the length of the spring if no weight was attached. Continuing, calculate the gradient of the graph, and there was some help. Increase in y over, which is length, divided by increase in x, which is weight, and so on. And finally, part 13, given that F is equal to kx, where F is the force applied, x is the extension, and k is the spring constant, the student were to use the gradient given in part 12 above to determine the spring constant, and the hint was something to do with inverse. The whole question carried 41 marks. Now you would note that in this example 2, the force point is not fixed. In the previous example, we had a fixed point here, which was 0, 0. Now this one, the first point is 1.0 and 0.070. So this is a little harder to do than if you have the first point being fixed. So this was a graph paper that the students had to use. So we will speed this up. As I said, if you don't begin with 0, 0, it's a little harder to do, and we will come back to this in a little while after we finish this example that we are doing now. So let's speed it up. We skipped a few stages, as you can see. We draw the first quadrant here. We put in the weight on the x-axis. We scale it out up to 7 newtons. We put in the scale and the sensitivity. Now, as it relates to this other axis here, you will notice that these numbers here are very, very small. So to make life easy for us, we will move that point there from the largest of the small number 3 places, and therefore consider all of this as the points being moved 3. It is easier for us to scale this out and plot the points. So this 0.070 becomes actually 70. This 0.086 becomes 86, and so on. Easier initially. So if we use this data, we have to draw a line of best fit. It's partially done here. As you can see, we are using this data up here. We scale this axis out. We scale this axis out. This axis we haven't scaled out exactly as required. We are temporarily using all the numbers as whole numbers, making this largest number the whole number. So we move the point 3 places, and every single number here, we will move the point 3 places. So that becomes 70, 80, 86, 104, 108, and 111. We will go back before we finish and put in the points. So this is just to make it a little easier for us. So we have scale out, we have all the points plotted. As you can see, here, somewhere here, the first part from there to there, we could probably get a straight line, and then a curved something like that. So we will complete this, and then we look at principles for straight line with no fixed point. So on the graph paper, so we did all of this. We have scaled out the axis, the x-axis. We have scaled out the y-axis, except we didn't use these points. We are using it a little easier by shifting the point in the largest number to make it a whole number. So we have this completed, this completed. We have this here temporarily, and we have all the points plotted, which is this. So we accurately plot all the points. Now this is what our graph will look like. From here to there, we will get a straight line, and then we have a curved part up on this point here. If you measure from here to there and from here to there, you will get a total distance as from here to there, there to there, and there to there. So we have total distance missed above equal to total distance missed below. So that's a very good line of best fit. So we draw the line of best fit. As I said, it's a little hard to draw, takes a little practice. And then we go back now and put in the actual values, put in the point in front of the 1.6, and we scale it out. Our scale is 0.010 meter per centimeter, and the sensitivity is 0.002. Now we have to bear that in mind as we plot the points. So we draw the line of best fit. Note that the last part is a curve, which is this. So we fill in the correct numbers on the y-axis. Okay, if you find this video useful, please like, share, and subscribe to this channel. Continuing, what is the length of the spring when the weight of 4.0 Newton is applied? So this is a graph that we have. So we know the sensitivity on this side is 0.002 meter. If we are starting at this point, 4 Newton, what is the length of the spring? Well, to do that, you come here, you draw some dashed line going up until you touch the graph at this point, and then you go across until you reach here on that axis. You read that axis off, and you get 0.098 meter. That's the answer to that question. So if you are given any value on the x-axis within the known data range, and our known data range is 1.2 to 6.0, we take any point here. Suppose it had been 2.5. We come here, go up here, go across, and that would have been our answer. That is if you are given the weight and you want to find the length. That is the principle you will do. This is called interpolation. That is to say, you are able to derive information within the known data range. And remember, our known data range is from here to there. Next question. What is the weight attached if the length of the spring is 100 millimeters? Now, 100 millimeters is 0.1 meter, which would be this point here. This time you go to the right, arrive here until you touch the graph, and you come down until you reach here, and you get 4.1 newtons. So given the length within the known data range, you draw a line, a broken line, until you reach the graph, and then you come down until you reach the other axis and you read that off. Now, as I said, this is called interpolation, where you are asked to derive information within the known data range. And of course, if you're given any other value, let us say within this known data range, let us say 0.90, and you want to find this one down here, the weight, you would come to 0.90, come across like that until you reach here, and then come down until you reach here, and that will be the answer. That is the principle that you use, given a quantity within the known data range on one axis, to find the quantity on the next axis. That is the principle you always use, provided you are within the known data range. And that principle is called interpolation. Now, the next part of the question says, what will be the length of the spring if the weight attached is 6.8 newtons? Now we have a problem. You see, 6 is here, 6.8 is here. If we go up at 6.8, if we go up at 6.8, we are going to miss the graph. So what do you do? Now remember, for interpolation, it is within the known data range. Now this is outside of the known data range. So we are outside of the range. So what you will do, remember we talked a little about extrapolation, where we will extend the graph in the pattern it is following. So what we will do is this. Our known data range is up to here. We will extend the graph here. So this is called extrapolation. We go beyond the known data range, and we use dashed line to indicate that we are doing extrapolation. We follow the trend of the graph. Graphs seem to be going like that. So we follow the trend of the graph, and that is our extrapolation. Now we can take this 6.8. We begin here 6.8. We go up, we reach this point, and we go across, and we come to that point there, which is 0.116 meter. So if you have to go beyond your known data range, you will employ something called extrapolation, which follow the trend of the graph. What is the length of the spring when no weight was attached? Now, when the weight is 0, which means when the weight is 0, which means we are here. Again, we have to do extrapolation, but we have to come this way towards the left, because it is outside our known data range. And so we used extrapolation on the right here. We are now going to use extrapolation on the left here. And so we get something that looks like this. We follow the trend of the graph. Notice on the left-hand side, the graph is going straight. On the right-hand side, the graph was curved. So we follow the trend of the graph, and we use dashed lines. We begin here because our weight is 0. What is the length? The length is 0.054 meter, which is this point here. So now we have looked at extrapolation, we have looked at interpolation. Next part of the question says that you are to find the gradient of the straight line part of the graph where it has not exceeded the elastic limit. Now at this point here, over here, the elastic limit has been exceeded. From here to here, we have a straight line graph, so the elastic limit has not been exceeded. So we need to find a gradient at this point. We choose two easy points to read, that one there and this one here. And as you can see, this point here is 1.4 and this point here is 4.3. That point there is 0.070, which is this, and this point here is 0.102, which is that. So the students were given a hint that the gradient is increase in y divided by increase in x. Now y started at 0.102 and ended at 0.070, so the increase in y will be 0.102 minus 0.70 meter, and the increase in x started at 1.4 there and ended at 4.3, so it will be 4.3 minus 1.4 Newton. You work that out and you get 0.011 meter per Newton. You have to state your unit. Clearly state the unit for your answer. And then finally, given that F is equal to Kx, where F is the applied force, X is the extension, and K is the spring constant, use the gradient from part 12 above to determine the spring constant, K, in Newton per meter, and the students were given a hint, something to do with inverse. So, this was the gradient of the graph. But this gradient here, we were dividing length by weight. Now to get the spring constant, we have to divide weight by length. So it's the inverse. So what you do, you actually find the inverse of that gradient that we had here. So 1 over 0.011, and this time it will now be newtons per meter, which gives us 91 newtons per meter. Now, if you want to verify that, you could just do this, but put this part here below and this part here at the top, and you will get back the same answer. And that is question 2 with 13 parts that the Form 3 students were supposed to do. It's not so difficult after all. Now let's consider one more thing before we conclude with this video. Now this was the one we just did and it curved a little, but let us say it didn't curve. You had to draw a straight line. But you don't have a fixed point, 0, 0. Now, you can use one of 3 approaches. They will not be exactly correct, but an approximation. And so we will look at the 3 things that you can possibly do if you don't have the fixed point, as in the previous example that we did for part 2. If you join the first and the last point as a first step and it's not working out, what you can do is you can consider the first point as fixed. Consider this first point here as fixed, and then all you will have to do is move that point a little this way or that way until you get your line of best fit, as in the first example that we did. That is one thing you can do when you don't have a fixed point. And of course, this is computer generated, and we have a very good R² value here, 0.985. Now here is another example where you could do the same thing. Again, consider this point here as fixed. Connect the first to the last point, and if it's not working out, just shift this point, that end of the line, one way or the other, until you have the estimated total points below, distance below 1, 2, 3, 4, 5, 6, until that total distance is equal to the total distance on the other side, which would be that plus that. And that will give you a fairly good line of best fit. And this one here was computer generated. So we know that is correct, that the R squared value is 0.942. So that's one thing you can do if you don't have a fixed point like 0, 0. Another thing you can do is, second thing you can try is join the first and last points, as we did here in red, but then you will notice that your total points on both sides are not the same. So you twist that line slightly. So that red line there, you bring it down a little this way. And this red line here, you twist it up a little that way. And you will find that you get that black line, which is computer generated. So we have a very good line of best fit with an R squared value of 0.981. Now, that's the second thing you can do. Now, remember I said that while you may get the points on both sides being the same, your R squared value may not be the best, but this is the best you can do physically without a computer. And in the third example, the third thing you can draw, or you could try, is you draw a straight line to touch as many points as possible, as in the case of this red line here. But you know that is wrong, because you hardly miss any point below that one, and you miss a whole lot of points far away on the other side. So once you do that, you shift the whole line parallel upwards somewhat and try it again to see that now you have equal total distances above as below. So that's a third thing you can do. Now remember, in all of this, it's an approximation. And while the total distances on both sides may be the same, that may not be the best in terms of your R squared value, but at least you give it a try. Now, those were 3 approaches to try. You will get equal total distances on both sides of the line, but your R squared value may not be the best, but at least you give it a try. Now, anything better than that, like you're doing SVA, say social studies or one of the other subjects, biology, and you really, really want a good line of best fit, you generate it using your computer. And I will give you one example of how to do that right now. So let us say you have this data, and we want to do a graph with a line of best fit. Highlight the data, insert up here, you go to charts, scatter chart, choose this one on the top here. And then you fine tune that by picking one of these other charts, maybe fine tune that by picking one of these other charts like that. And essentially, that's where you are. Expand it, make it a little bigger. We right click on one of those markers and you go to Format Data Series, Marker Options, built in. By default, it's a diamond shape. We will take an X, size 6, and that marker line color, we will give it a solid line of black. Move it to the side here. Then the mark itself, we will make it a little thicker, and we say OK. And now that is what we have. We have our graph. You can change the title of the axis. This here would be length, in millimeters. Make it a little bigger. Home, say 16. And this one here, you double click on it, highlight, make it 16, and this will be loaded in newtons. Now that you have that, you're basically finished. But we have to draw the line. So you go back to those points, right click again, and go to add trend lines. When you go to add trend lines, this box here comes up and you could have different trend lines. We already have it set on linear, which is the one that we want here. You could set it at exponential, logarithmic, power, polynomial, but the one we want is linear, which is our line of best fit. The line color, could make it a solid line color, and it is already black. Line style, make it a little thicker if you want. You get that. You can come back here, right click again. So we are here. Down here, we can include the equation if we like. Display equation on chart. So that is going to be the equation of this straight line here, which is our line of best fit, which we can use for a whole lot of things. And then we could also display the R squared value on chart. Once you do that, you close this, you go back here, you highlight this, and you go to home, we go to font size, make it 14. So that is the line of best fit computer generated, including the R square value, which is not very close to 1, so it has a lot of spread. And also you have the formula y is equal to 1.046x plus 16.13. And this is just for those who are interested in learning how to do this line of best fit using your computer. Many people may not be interested in this, but there may be one or two students. So this is for your benefit. And that brings us to the end of part 3 of Physics 23, the use of Hooke's law to demonstrate the line of best fit, especially if you don't have a fixed point, and how to use such graphs to derive specific information, including extrapolation.